halogenation of ketone and aldehyde at the alpha carbon. Ketone and aldehyde can react with halogen in dilute acid or dilute base to give monosubstituted product as racemic mixture. The formation of enolate is involved in the mechanism of this reaction as the following slide indicate. In the presence of base, enolate is formed. Also here, enol and enolate formed as Z and E isomer. Then halogen enolate attack halogen to give the monosubstituted product. The halogen is added on both E and Z isomers. If the halogen added to the same side of E and Z isomer, two enantiomer results, that's to say the racemic mixture is formed. Acid, we say here in the case of catalysis by base, we say that the reaction is base promoted. In case of acid, we say that the reaction is acid catalyzed. In this case, enol is formed also as Z and E isomer. Here is a aldehyde or ketone acid to give the enol in slow step. Enol attack halogen and add halogen. Also, the reaction take place in Z and enol if the attack takes place in the same side of enol, in the same side of Z and E isomer, we obtain 2 enantiomer. That's to say, the product will be racemic. The haloform reaction. In case of methyl ketone, in the presence of excess halogen and in the presence of acid or the base, substitution of the 3 hydrogen takes place to form trihalomethyl ketone. This intermediate can be easily hydrolyzed in the reaction medium to give the carboxylate and the haloform. This is the general equation of the reaction. The reaction starts with the formation of monosubstituted, and in the presence of excess halogen, the second hydrogen can be replaced by the same mechanism because it is more acidic than the first hydrogen, because it is attached to halogen. The reaction repeated twice to give the trihalo derivative, which can easily hydrolyze with water or with sodium hydroxide to give the carboxylic acid and haloform. The next slide illustrates the mechanism. First, halogenation step, base catalyzed, base promoted, form monosubstituted, then reaction, as we said, repeat twice. The second step, the second stage, acyl substitution step. Here hydroxide attacks the carbonyl and results in our bring acyl substitution to give the carboxylic acid and the carbonyl trihalocarbonyl. Carbonyl here is formed. This is rare case. A rare case is the carbonyl act as leaving group, but here carbonyl is stabilized by 3 halogen. Therefore, it can be formed easily. The last step, acid-base reaction between the carboxylic acid and the carbonyl to form the carboxylate and the haloform. In the following slides, we learn some things about enolate formation. First, consider the first equilibrium. Ketone, weak acid, plus ethoxide, stronger base, equilibrium to sodium enolate, stronger base, and ethyl alcohol, stronger acid. We recognize here the stronger acid and the weaker acid by the pKa, by knowing the pKa of the compound. Ethyl alcohol pKa about 16. Ketone pKa about 19. And you apply the fact that conjugate base of stronger acid is a weaker base, and conjugate base of the weaker acid is a stronger base. I repeat again, we must remember that the conjugate base of a stronger acid is a weaker base, and the conjugate base of a stronger acid, conjugate base of weaker acid is a stronger base. Thus here, the sodium enolate is a stronger base than sodium ethoxide. Therefore, the equilibrium predominates to left. Here, the stronger base is the enolate, and the weaker base is ethoxide. Therefore, the equilibrium predominates to left direction. Here is an equilibrium, and the equilibrium is shifted to left. The pKa of the conjugate acid of the weaker base is similar, nearly similar to the conjugate acid of the enolate, that's to say the ketone. We can then say that if the conjugate acid of the used base is weaker than the ketone, pKa about 19, this means that the used base is a stronger base than the enolate. In this case, the equilibrium predominates to right direction. Then consider the second reaction. Ketone plus LDA, stronger base, gives nearly irreversible reaction, gives enolate زائد plus diisopropylamine, weaker base. Diisopropylamine pKa 38, ketone pKa 19. Therefore, lithium diisopropylamide, LDA, that's the conjugate base of the weaker acid, diisopropylamine, will abstract proton from the ketone, and a nearly reversible reaction gives the enolate. We can exploit these facts in the synthesis as we learn in the following slide. Before this, we learn some definitions. Before this also, we should learn the preparation of our strong base, lithium diisopropylamide. Diisopropylamine pKa 38 plus butyl lithium, very strong base, give acid base reaction to give the lithium diisopropylamide, our strong base, abbreviated LDA, and butane. Very rapid, very fast reaction. Here is 2-methyl hexanone and we learn how we prepare the enolate from the methylene group and how we prepare enolate of the methane proton. The enolate formed in equilibrium as the first reaction we considered this session. The enolate formed in this equilibrium is called thermodynamic enolate. It's formed in equilibrium reaction. We remember that the pKa, the conjugate acid, the base, and the ketone is nearly similar. Therefore, the equilibrium takes place. And this equilibrium, we lies predominant favorably towards left, as we say. This enolate is called thermodynamic enolate. We say that thermodynamic enolate is that which is most stable among enolate. Enolate stability is evaluated in the same way that in alkane, that's to say, the more highly substituted enolate is the more stable. Thermodynamic enolate predominates under conditions where deprotonation-protonation equilibrium allows interconversion among the possible enolate, such that eventually the more stable enolate exists in higher concentration. This is the case when pKa of the conjugate acid of the base is similar to pKa of the hydrogen of the carbonyl compound. This condition is attained when we use hydroxide or alkoxide in borotic solvent. In this condition, thermodynamic enolate predominates. Kinetic enolate. The kinetic enolate is that which is formed fastest. It is usually formed by removal of the least sterically hindered alpha hydrogen. Kinetic enolate predominates under conditions which do not form equilibrium among the possible enolate. That is the major thing here. We must remember that exactly. Kinetic enolate predominates where conditions which do not favor equilibrium among the possible enolates, that's to say, under a reversible reaction condition. This condition is attained when we use very strong and sterically hindered base in an abrotic solvent, such as lithium diisopropylamide in tetrahydrofuran. Note that we must use abrotic solvent such as ether or pentane in hexane when we use such stronger bases, because if we use abrotic solvent, the reagent, the strong base which you use, will react vigorously with this abrotic solvent to give diisopropylamine and liberate the alkene. And liberate the alcohol or water if we use abrotic solvent. Again, we must, if we use lithium dipropylamide LDA, we must use abrotic solvent, because if we use abrotic solvent such as alcohol or water, the reagent will vigorously react to the solvent and disappear to form water, to form hydrogen in case of water, or alcohol in case of to form hydrogen in both cases, and hydroxide in case of water, and alkoxide in case of alcohol. Then we apply these concepts in the formation of inulate from the 2-methyl cyclohexanone. Here is 2 position for the proton abstraction, either from methylene group or for methane proton. If we use weak base in abrotic solvent such as sodium hydroxide in water or sodium isoxide in ethanol, this condition favors, as we have just said, the formation of thermodynamic inulate, because here equilibrium takes place in both sides of the reaction, either from methylene group or from methane proton, the equilibrium established in both reactions, but the more stable enolate predominates because it is more stable. That's to say, the thermodynamic enolate predominates in this reaction, in these two reactions, in these two equilibrium. These two reactions brought by the same reagent, abstraction from methylene group, or abstraction from methane group. If we use sodium methoxide in ethanol, the more substituted enolate will predominate. If we use diazopropylamide, dimethoxyethane solvent like tetrahydrofuran, a protic solvent, here irreversible reaction. Only one reaction, irreversible reaction, to form the kinetic enolate, which is formed fastest by the very strong and strictly hindered base. In this case, diazopropylamide. There is the enolate formed faster because the hindered strong base removes the less hindered proton faster. This is logic. Direct alkylation of ketone with lithium enolate. Then we exploit all these facts in synthesis. If we want to alkylate dimethyl ketone, methyl ketone to methyl ketone at the methylene group, we must use lithium diethylamide to prepare or to obtain the kinetic enolate, and then added the alkyl halide. We must use primary alkyl halide, or primary benzylic halide, or allylic halide, because this base, lithium diazopropylamide, is very strong. If we use secondary or tertiary alkyl halide, elimination in the halide takes faster than enolate formation, and the reagent consumed in undesired reaction. So we use always primary alkyl halide. Another reaction of enolate is called aldol reactions. Aldol reaction is a reaction between two molecules of aldehyde or two molecules of ketone in dilute acids or alkali to form beta hydroxyaldehyde called enal, called aldol or beta hydroxy ketone. You can call it also aldol product, aldol addition product. Aldol reaction is very important reaction in organic synthesis because it forms CC carbon bond. Then we consider the reaction mechanism. Mechanism for aldol addition in basic medium. First step, formation of enolate, alkali abstract proton to form enolate anion stabilized. Then addition of the enolate in nucleophilic substitution reaction to another molecule of aldehyde or the ketone to give an alkoxide anion. Alkoxide anion in the third step abstract hydrogen from water and to give the aldol product. Note that all of these reactions in this medium are reversible. Ketone doesn't undergo this reaction because the steric hindrance in the addition step. Therefore, ketone unfavorably form addition aldol product in alkaline medium. We can perform the aldol addition reaction from ketone in acid medium, as we will see. Then, because the addition reaction is a reversible process, then we can find what is called retro-aldol reaction, in which the ketone, the product from the ketone, aldol addition product from ketone, undergo reversible reaction to give the starting ketone in basic media, alkali. Note that the equilibrium here is shifted towards formation of the ketone. The mechanism for retroaldol reaction here. First, removal of hydrogen by hydroxide and form the alkoxide. Alkoxide liberate the enolate and form the starting ketone. Enolate abstract proton to give another molecule on the ketone. Aldol condensation reaction. The aldol addition product, when treated with dilute alkali or just heated in water, can undergo dehydration to form 2-butene from the acetaldehyde to form 2-butenal. The form class we name enal. En for the presence of double bond, al for the presence of aldehyde group. All products ended with the final enal. Here we see the mechanism: extraction of proton to form the enolate. Enolate liberate the hydroxide. Note that the hydroxide ion formed here as a leaving group. Hydroxide here act as a leaving group. This is usually abnormal, but takes place here because the stability of the formed end product, conjugated ketone, stable. Therefore, this reaction is irreversible, and OH leave as leaving group. Normally, it is not a good leaving group. We call this reaction condensation reaction, because definition of condensation reaction is a reaction in which small molecule liberated, here water, is formed as byproduct. acid catalyzed condensation. I have said that acetone, ketone, cannot undergo or don't undergo aldol reaction in alkaline medium. We can carry out the aldol condensation directly in acid medium. For example, 2 molecules of acetone, the presence of HCl, treated with HCl, give the first the addition product, and then the addition product undergo elimination of water to give the condensation product for methyl bent to bent 3-ene 2-one. This class of compound is called enone. Here, the mechanism for acid catalyzed formation of condensed aldol product. The mechanism, first step is the formation of enol, acid catalyzed formation of enol as usual. Then enol attacks the protonated carbonyl group to give the protonated aldol product, aldol addition. In this product, proton transfer takes place to form protonated hydroxyl group, which can be removed as water, and the result is the formation of alpha beta unsaturated ketone. Here is an application of aldol reaction in organic synthesis. That is the synthesis of butanol in 1-butanol in industry from acetaldehyde. Acetaldehyde treated with 10% sodium hydroxide, temperature below 10, at 0 to 10, gives addition product. Addition aldol reaction product, beta hydroxyaldehyde. Note that low temperature here is important, because at higher temperature dehydration takes place. Here aldol product heated to give here 2-butene-1-al alpha beta unsaturated aldehyde, which can be easily reduced by hydrogen in running nickel at high pressure to give 1-butanol. Here is some synthetic application of aldol reaction. Aldehyde, starting with aldehydes, base, and alcohol, aldol addition product. Sodium borohydride give reduction of the aldehyde group to give 1,3-diol. An aldol treated with acid to bring about dehydration to form alpha beta unsaturated aldehyde, which can be easily reduced. Only the carbonyl group reduced with lithium aluminum hydride to give allylic alcohol, an important synthetic compound. Both aldehyde group and the double bond can be reduced with hydrogen in running nickel at high pressure to give saturated alcohol. Alpha beta unsaturated aldehyde can be hydrogenated selectively at the CC double bond to give long chain aldehyde. Start with aldehyde containing certain number of carbon. Here is the double number of carbon. This is the value. This is the value of aldol reaction. CC bond formation.